Hello everyone, welcome back. So, if modern electronics had a heart, it would be the semiconductors. It is the one material that doesn't behave like metal and doesn't behave like insulator, yet quite powerful. And everything starting from phone to medical devices are made with that. So let's understand what makes the semiconductors so special. Electronic devices. So a device in which conduction takes place by movement of electrons through vacuum, gas, or a semiconductor. Electronics, simply put, is the study of how electrons behave under different conditions. So now moving on to semiconductor physics. So let's start with conductors. Conducting materials like copper or aluminum are good conductors of electricity. They are known for having large electrical conductivity and very small electrical resistivity. To put the number on it, so the resistivity of the conductors is about 10 to the power minus 8 ohm meter. Now moving on to insulators. Insulator materials, for example, porcelain, glass, and quartz, are just opposite. They have very poor electrical conductivity and very large resistivity. So we use them to block current flow. Their resistivity is roughly 10 to the power 12 ohm meter. Then moving on to semiconductors. So semiconductors sit between conductors and insulators. They are neither great conductors nor perfect insulators. Like at room temperature, semiconductor conducts more volts than a metal, but a lot better than an insulator. The typical resistivity range of a semiconductor is 10 to the power minus 4 to about zero point 0.5 ohm meter. An important thing to remember, the resistivity of semiconductor is not fixed. It depends on several factors and causality. It can be controlled. For most conductors except carbon, the resistance increases with temperature. Insulators, on the other hand, usually keep most of the same resistance over some temperature range, and then suddenly they can break down and start conducting. Insulators behave differently. As temperature goes up, the resistance of the semiconductor goes down. That means semiconductors have a negative temperature coefficient. So to sum up, conductors are having low resistivity, insulators are having high resistivity, and semiconductors are in the middle, with a neat property that we can tune their resistivity and their resistances fall as temperature rises. So now moving on to semiconductor materials. The semiconductor materials are primarily composed of silicon and germanium elements, and silicon doesn't occur naturally in the free state. It is most abundant element after oxygen in earth crust. So it occurs in combination with oxygen as silica. So SiO2, silicon dioxide, and silicates. Then moving on to germanium is an earth element and it is recovered from the ash of certain coals or from the flue dust of zinc smelters. So generally recovered germanium is in the form of germanium dioxide, which is reduced to pure germanium. So let's move ahead. So next is crystalline structure. Think of a solid or something that is packed tight. Molecules, atoms, or ions pressed closer together, held by strong forces. That's why the solids are rigid, hard to compress, and mechanically strong. Now, when scientists shine X-rays through a crystal, something beautiful shows up. The atoms are not random. They are arranged in a definite repeating pattern that fills the whole three-dimensional space. Now moving to crystal lattice and unit cell. To describe where each atom sits, we use point in space. This area of points is called as space lattice or the crystal lattice. So basically the 3D map that tells you how atoms, molecules and ion sheaths relatively to one another. Picture it like this. Each point on the lattice represents the same atom or the same group of atoms repeated again and again. This repetition is what gives a crystal in regular structure. The smallest block which when repeated builds the whole lattice is known as the unit cell. Think of the unit cell like a single tile in the floor, tile 1, tile 2, tile 3. Keep repeating and you will get the entire pattern. Only here is the twist. The wallpaper analogy people used in 2 dimensions. A lattice is the same idea but in 3 dimensions. So in short, solids are tightly packed. X-rays reveal the packing in often perfectly ordered. Crystal lattice is the 3D map of that order, and the unit cell is the smallest repeating tie that builds the whole crystal. So at the atomic scale, whether a material passes current or blocks it, that decision is made by how atomic neighborhoods share the electrons. So to moving forward, the energy band theory. A crystal is nothing mystical. It's just the same structural unit repeated over and over in 3 dimensions. When we talk about electron in a single free atom, they have discrete energy levels, the well-known shells and subshells, right? So, but put that atom inside a crystal and picture changes. Why? Because the potential that an electron sees in the crystal is not the potential of all atom alone. It is a periodic function in space built from contribution of every atom around. Now one important point to start with, the inner shell electrons, the ones tightly bound close to the nucleus, are hardly affected when atoms join to form a crystal. It is the outer shell electrons that changes a lot, because these are the electrons that get shared between neighboring atoms. So what happens to those outer electrons? So if we solve the quantum problem for the crystal, we don't get isolated atomic lines of energy anymore. Instead, because adjacent atomic wave functions overlap and because of Pauli's exclusion principle, many original identical levels split into huge number of closely spaced levels. Collectively, these many levels form what we call as energy band. So let me give you a picture to hold you in mind. Imagine a crystal made of n identical atoms. Say the group 4 elements containing carbon, silicon, germanium, tin. These are just examples. So if these atoms were very far apart, so far that they don't interact, then each atom keeps its atomic energy level and nothing changes. Focus on the outer subshells, the S and P levels. Each atomic level degenerates across the n atoms. That's why we say there are 2n S states and 6n P states, for instance. Now slowly bring these atoms closer together. So their wave functions overlap and degeneracy lips. The 2n identical S states spread out into S band and continuous regions of many closely spaced energies. Similarly, the P also spread into a P band. Between these bands, there may or may not be a gap. If the bands are separated, we have a band gap, as we can see here. The regions of energies that electron cannot occupy are called as the band gap. If these bands overlap, the electrons can freely occupy across the overlap, and that's the hallmark of the matter. In many covalent crystals, think of silicon and germanium, the lower band is formed by the occupied states is called as the valence band, and the higher band, which may be empty at zero temperature, is known as the conduction band. This energy difference between top of the valence band and the bottom of the conduction band is called as the band gap, which is given by Eg. As you can see here, this represents the Eg. A useful way to think about chemical valence here: when the S and P bands mix and form the valence band, each atom effectively contributes its outer electrons to the crystal collectivity states. For the group 4 example, each atom gives up 4 outer electrons to these bands, which is why we say that tetravalent in the solid. Finally, the size of the energy band gap and whether bands will overlap depends on how close the atoms are and how they are oriented in the lattice. So in short, isolated atoms have different energy levels. Crystal turns those discrete levels into bands. Because of interaction and Pauli's exclusion principle, the valence band and conduction band are separated by a band gap. And that band picture is the foundation of understanding of insulators, semiconductors, and metals. So if I want to explain this with respect to the diagram, as we have seen, so initially whenever the atoms are far apart from each other, then there is no force of attraction between them. So that is, at that state we are having the outermost shell electrons, as you can see here, the 2s electrons and 2p electrons. And similarly in all the cases like carbon, silicon, germanium and tin, we have 2s2 and 2p2. Here also we have 3s2, 3p2, 4s2, 4p2, and here we have 5s2, 5p2. So actually we are having 2s electrons and 2p electrons, but the states, if we say, we have 2s states and 6p states, out of which 2s electrons are filled, and out of 6 states 2p states are filled. So we can say here, whenever they are far apart from each other, then there is no force of attraction, so they are separated from each other. But when they are brought closer, then the energy will start increasing, and it will, after a certain period of time, when we bring them far closer, then they will overlap with each other and all the energy states get combined. That means 2s states and 4p states, 6p states will get combined, and totally we have 8 states, and we have total number of electrons as 4. So during this process, as we have already said, that there is exist energy gap in between them, and depending on the material, it may be overlapping or it may be with an energy gap. So that energy gap divides the states into two equal parts. First one is 4n states on the top, and the second one is the 4n state at the bottom. The upper part we call it as the conduction band, and the lower part we call it as the valence band. The electrons will settle in the lower part, that is why we have them in the valence band. So now if we represent this with respect to this diagram, then these are the corresponding energy band structures with respect to insulator, semiconductor and conductor. So in the conductor we can see that there is no energy gap, both the energy bands are overlapping each other. In case of the insulator, there is a very high energy gap, which is with the value within the range of 6 electron volts, and in case of semiconductor we have 1 electron volt gap. Now the upper terminal or upper band is known as the conduction band, and the lower band is known as valence band, and all the electrons are present here in the valence band. Now for conduction to take place, the electron will have a affinity to move towards the conduction band. So whenever they reach the conduction band, then we say that current is flowing. So to have that, this energy gap is to be overcome. So that is why it is also known as forbidden gap. So to move further, we'll again see what is this forbidden gap, or how much or how far the electron can go within this range, So that will be discussed in our next topic. So moving forward, next is Fermi-Dirac functions. So it specifies the fraction of all states of energy occupied under conditions of thermal equilibrium. That means the energy level which the electron will possess is known as the Fermi level. So it is given by, mathematically it is given by F equals to 1 by 1 plus e to the power e minus ef by kt, where ef is called as the Fermi level and E is the energy possessed by the electrons. So now if we consider E equals to Ef, that means the energy possessed by electrons is equals to Ef, that is the Fermi level, then this e to the power 0 term will become 0, this term will become e to the power 0 is 1, so we'll have 1 divided by 1 plus 1 is half. So that means Fermi level will exist in the middle. So whenever the value of energy obtained by the electron is equals to Ef, then we have the Fermi level in the middle. Now consider a state when the energy is above Fermi level. So above Fermi level, can the electron attain anything? So if we put that here in this equation, then this term, since value of E is very much higher than Ef, so this term will become e to the power this is a very higher value, so which will be given as infinite. So 1 by 1 plus infinity, this will become as 0. So that means no electron will have any energy, or no electron can move beyond the value of the Fermi level. Now let's move into the third condition, that is below Fermi level. So let's see what electrons can attain. So in this case, if we put E very much less than Ef, then this term will be negative, so e to the power minus infinity, so this term will become 0. So 1 by 1 plus 0 is 1, that means it is having full probability, that means electron will definitely have all the energy levels below Ef. So this is what Fermi-Dirac function is. Now according to Pauli's principle, which states that there are no two electrons may have the same set of quantum numbers at 0 degree Kelvin, right? So therefore electron would actually have all the energy starting from 0 to Ef. So it will reach from 0 to Ef, all the electrons will have different energies, right? So at higher temperature, few electrons will have significantly higher energy level, and at the lower temperature they will have slightly lower values. So if we increase the temperature, then this Fermi level will slightly shift or slightly change in this format. So for example, this straight line represents at 0 degree Kelvin, then this is the this dotted line represents at 300 degree Kelvin, and this line represents the Fermi level at 2500 degree Kelvin. So the Fermi level slightly shifts or moves upward, because it is obvious that all the electrons will try to move from valence band to conduction band. So whenever we increase the temperature, so they will have a affinity to move faster from valence band to the conduction band. So that is why Fermi level is also slightly changing its position and is shifting towards the conduction band, so that the conduction will take place. So if you consider this diagram, then as the area under the curve represents total number of free electrons, so it can be given by, so using this formula we can determine the value of all the free electrons. So from this, if we determine the value of Fermi level, it will be represented by so it will be represented by 3n divided by 2 gamma to the power 2 by 3. So this is the value of the Fermi level, considering this value, where the value of n varies from metal to metal. So this is the Fermi-Dirac function, and the Fermi-Dirac function or the Fermi level is the highest attaining level that can be occupied by the electron. So next we will see, this is for the level that can be attained by the electrons to the Fermi level. So in our next discussion We'll try to see the concentration of these electrons with respect to if we are considering n-type or p-type semiconductor, and also if we are having intrinsic semiconductor and extrinsic semiconductors. So that will be the discussion of our next class. So thank you for listening and keep joining our classes. Thank you.